Oh, hey guys, this is the solutions to the first homework assignment. This is, I'm going to do all four real quickly. I'm just going to go over them like I would in class. Ignore this textbook number and problem number. That's what we use in our old textbook, but the questions are still the same. I'm still using them because they're pretty good. First question one was a simply supported beam with just concentrated loads, and we did 2 or 3 examples in class. This is what I wanted to show you. Just the solutions of it, but basically that's your loads, and your shear diagram goes up 1557.1, goes over constant, 2500 down, right, constant, 1742.9 up, over, and then 800 down, closes up. If you do the at point A, B, C, D analysis just like we did, you find that the maximum bending moment, or the bending diagram, has 2 peaks. And obviously the sign isn't that important in the moment diagram. It just means which way the moment is turning, but the magnitude is what you're concerned with. The max moment was found at point B at 6228.4. That's the max bending moment. Also, here are the reactions down below. We didn't know RA and RC, and once again, we found the reaction at A was 1557.1 and RC was 1742.9. It's important to get these right. In fact, it's vital. If this isn't in static equilibrium, before you do this method, you will not get the right answer. No way, no how. So that's it. I'm sending a PDF or an email of these as well, so you can go through it. But basically, the solution shows why we use positive and negative signs in the moment calculations, and you'll see where the numbers come from. I think this is a very easy example, and you should have no problem. All right, number 2. Same thing. Like I said, ignore that textbook number. That doesn't apply to you guys. Another one where we had a simply supported beam. Here's the reactions below. We had reaction at E and a reaction at B. The 2 of them were unknown. Solving for them, we get this in equilibrium. Here's the end forces: 12.5, 37.39, 15, 8.4, 38.29, 20. If we do our shear, up 12.5, over, down 37, over, 15, up 15, over, down 8.4, over, up 38.29 to 20, and 20 closes us up. The solution for the moment is got a couple of peaks. Obviously, there's a maximum here, 31.25, and a maximum here, or an optimum there, minus 50. The minus 50 is bigger. This is the value you would put when considering the maximum bending stress right there. So, and once again, this will be emailed, so you'll see all the math involved to this. This is a simple problem, and looking at all the videos and trying to do the ones in class, this problem should really not be any issue to anyone. But like I said, if you have any problem, call me, and I'll be happy to walk you through any part of it. Okay. Number 3 was a cantilevered beam. Okay, just like we did in class. It had a little, the one in class I think had 2 loads. This one has 3. Here's the first thing you got to do is the reactions. So the problem was given to you as 20 kip, 15 kip, 10 kip. So 30, 45 going down. As in any cantilevered beam, you better have a reaction at the wall where it's connected going up. That's obviously, if 45 is coming down, 45 must be going up. And you need a bending moment to counteract all the spin of these 3 forces doing that. You need a counteractive bending moment to keep it steady. That comes out to 320 kip feet. Shear diagram's easy, right? Up 45, over, down 20, over, down 15, over, down 10, closes up. The moment diagram, the only caveat on a moment diagram for a cantilevered beam is that it doesn't start at 0. It starts out at 320 kip feet, okay? And that's where it began, right there, okay? Then went to 140, then 40, then closed up. So this is the moment value that you would put into a bending stress calculation, okay? Number 4 was the most complex of the group. First is the reactions. Let's do that. So we had simply supported beam, RA and RB, right? And we had a concentrated load only on one side of it, 45 pounds per inch over a span of 8 inches, right? And we had reaction RA and RB. We got to convert this 45 pounds per inch over 8 inches to a 360 pound concentrated load right in the middle at 4, right? We'll be right there. Okay, we find that RA and RB, RA is 240 pounds and RB is 120. Notice that 360 total going down better equal 360 total going up. Static equilibrium, we're good to go. Okay, now we get here. Shear diagram would go up 240, right? We start there. Now we start the distributed load, right? We can't just go constant because it's not a concentrated load, it's distributed. So we got to go down a total of 360. From here to there, we got to go down 360. So 240 minus 360 is minus 120. We draw the line straight. The question is, where is point D, right? So we have points A, B, C. I made point D. If you go here, point D is right here. Where does the distributed load cross the x-axis? So we do the equation starting point minus the slope, which is that value of the distributed load right there, times x. X is equal to 5.33. That means this distance is 5.33. That means if this whole distance is 8, if this is 5.33, that must be 2.6667. You get the idea. Anyway, once you know these dimensions, now you're able to calculate the bases of these triangles. We call that triangle 1, triangle 2, or area 1, area 2. And we're able to calculate those areas down here, base times height over 2, 640 inches squared, base times height over 2 right there. And then we're going to use those area calculations in the moment numbers to get these points right here, right? So, for example, the moment at C is equal to the moment at B, the moment at D, minus A2. Area 2 is below the x-axis, so we're going to subtract it, and we get 480. That's 480 there. So we're going to go from 0. Remember, it's not a cantilevered beam. All moments are going to start at 0. We go up to 640, which is this calculation right there, down to 480, and then down to 0 we close. Since this is a first order curve, right? This is 0 order, this piece right, that's 0 order. That's first order, straight line. If that's first order, this must be second order. So what I really should indicate there is a comment. These all should be second order. That tells me that you know it should be a second order curve. And even if you draw it, you know, not so good, I know that you know what you're talking about. So anyway, here is the max moment. That's where we would calculate sigma equals MC over I. So on this beam, this is where the most bending stress occurs in the middle of point, not in the middle, but at D. So somewhere 5.33 from the left, right here is the worst possible place in that loaded beam for bending stress, okay? Any questions, call me up. I'm gonna post additional homeworks tonight and go through some more examples, okay? Thanks.